There is a somewhat special term that shows up quite frequently in math and physics called boundary conditions. So boundary conditions might be a word that you've seen before in a different class, and it's going to be something that we talk about right now. But I want to stress that boundary conditions are not only something that occurs for a wave, it's actually something that occurs in other situations as well. And so fundamentally, it's about putting a constraint on the value of a function or the derivative of the function. So effectively, we can say that I have some variable x, which is going to be my function, at some specific value. Or perhaps, and maybe this will be 0. That's frequently going to be our boundary condition. Or maybe we know that there's some other value that the derivative of our function evaluated at a specific place must have. So boundary conditions are just basically saying the value of your function, and in some situations the derivative of it, must be equal to a certain thing. And the basis of this, i.e. why do we know that it's true, is going to be purely conceptual. In that case, meaning physical. You can really think through where it's coming from, and there's a physical reason for it. But we're always going to express that mathematically, which is what I mean by up here. So a simple example of this is that our string is held down at the wall. The physical or conceptual basis is that your string is tied there. It literally cannot move. We're then going to call that a boundary condition and turn that into a mathematical expression by saying that the displacement at a position where it's tied to the wall is equal to 0. So this is something that's going to seem a little bit formal, like why do we have to use this fancy term? But again, it's a general idea that comes up in different situations. So if this is the first time you're seeing it, realize that in future math or physics classes you might see the term come up again. But simply we're going to take an idea, turn it into math that says what value our function must have at a point. That's all. So what's a specific boundary condition we want to think about? Again, this is going to be the string being held at the wall. So let's draw what this is going to look like. I have a wall, and one thing we sometimes do is trying to shade it to say, okay, this is a wall. And we're going to imagine that these are, ideal walls. They don't bend, they don't move, they don't break. We're going to say that the string is held at each end. So we have a string that is stretched between the wall. So I've basically just drawn its equilibrium position. Now, then we want to define a coordinate system as normal. And what we typically are going to do is call the positive direction, x hat to the right, call our left wall x equals 0, and call our right wall x equals L. So that is just saying that the spacing between these is L. That's a common notation we're using. So the other thing to recognize is that our boundary condition here is going to be true for all moments in time. It isn't that our wall is moving or anything. And so remember that waves are defined in both time and space. So we're defining something that happens at a specific location, right? We have one location, which is going to be the displacement at x equals 0, which is here. We have another displacement, which is x equals L, which is there. We're saying that there, the value must be 0. So I can draw some different sorts of waves, but they need to actually have the end be 0. If instead I imagine a different string stretched between the same walls, and I go to draw the function and I say that my function looks like that, well, you can say, well, this is clearly wrong because the end of my string needs to be tied at the wall. So that's the idea here, that this cannot be a valid wave because my end is not at the wall. That's all we mean by boundary conditions. And again, this is something that's true at all moments in time. So frequently when we think about these boundary conditions, we aren't going to talk about time since it's always true. So again, some fancy terminology, but what we're doing might feel a lot like common sense, and you wouldn't be wrong. This is when it suddenly gets a little more complicated. So because we've said that it's tied at the end of the wall, and again we can imagine drawing our equilibrium line and saying that our wave must be 0 at each end, if we're dealing with a sinusoidal wave, which is what we want to think about and is going to be true for our standing waves, then we know that at the value of 0, so again this here position is going to be x equals 0, that the value needs to be 0. Well, if we have sine of 0, right, because think about the fact that we have sine of k times x, sine of 0 equals 0, and that's always true. So just by using a sinusoidal function, meaning literally sine, we know that the point here is 0. So the interesting point is coming here at x equals L. So we've taken kx and plugged in L for it, and this is just our amplitude out front, 2a, which was coming from when we derived a standing wave from two traveling waves. So we're left with sine of kl, where L is the spacing between the walls, must equal 0. And again, this is because that's going to be our displacement at, in this case, our specific value of x equals L. What that means is we're going to get a condition that actually is coming on k. So we know then that for this to be true, we have to have KL equaling 2 pi, or say just pi, and multiplied by some integer, right? So whatever's here on the inside could be pi, 2 pi, 3 pi, 4 pi, etc., but that would be sufficient. So when you use how k relates to lambda, you then get this new condition, which is lambda equals 2L over m. And m here is this integer, 1, 2, 3, 4, and so on. So if we plug in different values of m, we get different values of lambda. And these are our allowed standing waves that are going to give us sinusoidal functions where we always get back to 0 at x equals L. And there's going to be an infinite number of possible m's. Here I'm only showing 1 and 2, the book shows 3 and 4, but you could imagine having m equals 11, m equals 27, m equals 1039. So we only have certain value of wavelengths though that are allowed, because otherwise, for instance, you could have it go up, come down, and up. Again, it's not back up at 0, so that's bad. So that's why we only have certain allowed values of wavelength. If we have a sinusoidal function, you must be getting back to 0 when you're at the other wall. Once we know that we have certain values of wavelengths allowed, we then plug that in to the equation that relates frequency to velocity. And remember that in this case, this is going to be the velocity of our wave. So if we're talking about a string, this is the speed of the wave on the string. And in that case, we plug that in and we then get a constraint on our frequencies. So because this is fixed, right, this depends on the string, we know that there are only going to be certain vibrational frequencies where you get a standing wave. If you put in a different vibrational frequency, you just don't get a standing wave. And this is something that, again, if you see it demonstrated in front of you, makes a lot more sense. But effectively, do you see this big old sine curve happening on the wave, or do you just see a straight line without any serious vibration? That's really going to be the difference between a standing wave and not having a standing wave. So hopefully this is clear. Make sure that you understand why only certain wavelengths are allowed. That's coming from this simple spatial constraint. And then that leads to only certain frequencies being allowed since your velocities or your wave speeds are fixed.